Okay. Well, welcome, everyone. Welcome, presenters and listeners. My name is Clement Fortin. I'm from the Skolkovo Institute of Science and Technology in Moscow. And it is a great pleasure for me to share this session. Yes, Mario, did you try to talk to me?
I can hear you. I can play whenever you want.
Okay, good. All right. So welcome. And then we have a full session with my paper. And therefore, I think we should move ahead as quickly as possible. And it is a great pleasure for me also to tell everyone that we have one of our papers, the fourth one, exploring challenges with designing and developing shore control centers for autonomous ships, that will be presented by Erik Veitch. I guess that's how you say it. Was selected as a reviewer's favorite. So congratulations for this. And of course, we will listen to all our papers very carefully. I think we have a great session. So Mario, we can start with the first paper.
Dear ladies and gentlemen, this presentation is called Fault-Tolerant Design of a Shifting System for Autonomous Driving. My name is Ralf Stetter and my co-authors are Richy Göser, Sebastian Gresser and Markus from Ravensburg-Weingarten University in the very south of Germany, and Professor Marcin Witczak from our cooperating Polish university in Zielona Góra. I will talk about what we understand under fault-tolerant design. I will briefly explain the gear shifting system, which is our example product, and I will talk about measures on 3 different levels, which you will see soon when I explain fault-tolerant design. So fault-tolerant design is design which aims to make products and technical systems more fault-tolerant, which is very well known is if you use redundancy. So for example, for aircraft with 2 engines, they are redundant. If one fails, you are still able to land. But there are many more possibilities if we look at abstract levels. So these abstract levels, they are very often used in design and in systematic design, and we can look at the physical structure. So we can look for physical diversity, or we can look for functional diversity in order to be able to develop technical systems which are more fault tolerant. Fault tolerance is extremely important because in today's products we have more and more electronics and the systems are getting more and more complex, and therefore we have a higher chance of faults. So we have to do something, and here this initial systematic approach towards fault tolerant design is intended to help designers to do so. What is our example system? It's for formerly a student race car, and it's for a driverless car. So we need the automated shifting system for our original gear set, which is from a motorcycle engine, from a Honda CBR 600. So what we developed here is an electrical motor with a position control. It has sensors and encoders, and we have a long shaft. Then we have a pair of spur gears. We have a star with a position and spring. We have the nearly original shifting drum, and we have additionally a potentiometer, which allows us to know the rotary orientation of the shift drum. And it is very important that such systems are fault tolerant because reliability is extremely important for success in Formula Student. So we had here measures on the geometrical level. So we have redundancy, 2 different sensors for position information. We have additionally switching star, which also ensures that our gears are engaged, and we have overactuation. So we can here achieve 6 Newton meter in this electrical motor, which is gear system, and we only need 1.5. So we have a better control quality to this. We have also measures on the physical level. Again, this is the redundancy, but we have 2 different sensor principles. We have one with a trigger wheel, which is inside the motor, and the other one in the potentiometer, which is using resistance in an analog way. Another thing on this physical level is that we have a fault detection through position control, through it means that through the position control, we can detect if we have a fault, which you can see here in the solid line. We also have measures on the functional level. We were investigating this in deep using a well-known framework, the EFM model. Here you see the whole framework with different views, and here an example of the main view, which you can also find in the paper. And what we came here, we have one important challenge, which is a tooth-on-tooth situation. So we cannot engage a gear because we have a tooth-on-tooth situation. And here we are able to detect this, and also by electronical means. Therefore, we are on the function level because it's not mechanical, and it's also based on effect, but it's electronical. And we can just re-engage this very quickly. We don't go back the whole way and have so a very quick reaction in the case of this fault. Thank you very much for your attention.
Good day, everyone. My name is Penny Kong, and today I'll be presenting my paper, Closing the Human-Machine Disconnect, Design Requirements for Two Extreme Companions for Future Autonomous Mobility. The background of this paper starts with the automation of future mobility, where the lack of a human driver leads to gaps in customer care and information provision on autonomous vehicles. Now, existing work on human-machine interfaces in this area tend to focus on either private vehicles or navigation and route information provision. As such, our aim is to design an interface that connects the autonomous bus and passenger in a way that evokes positive emotions, and this is done in the context of future public transport in Singapore. For our methodology, it consists of three major components. So before the survey, we conducted a benchmarking study to generate a list of possible attributes for a future mobility companion. This was followed by the survey, where participants were asked to select their preferred attributes and qualities to build up the ideal companion. These attributes were sorted into three categories based on the Kano model of product innovation. So participants had to select their must-haves, good-to-haves, and ideal-to-haves, and additionally, some companion qualities such as personality and appearance. Following this, they were asked to decide whether they prefer their companion or a human service staff for different mobility scenarios. Based on all this information, we then developed companion concepts based on the results. So from the survey, we see that these are the top 10 ideal to haves and must haves based on participant selections. As you can see, there are some overlaps between the two, but the ideal to haves tend to relate more to the personalization and customization of service, while the must haves are more focused on travel information. So for the assistant preferences per scenario question, we see that for most scenarios, the companion that participants had designed was selected as the preferred service attendant, and it was only for the scenario where participants were unwell did they select a human staff as their preferred attendant. For the open-ended question, one participant said that they preferred human-based interaction for health concerns, for instance. So this could be one explanation for the choices. And based on the results on the preference for assistance that you saw in the previous slide, we also combined it with the selected qualities of the companion. And we see that 71% of participants actually chose human assistance in at least one scenario, while 29% relied on the companion for all the scenarios we showed them. Within this group of 71% of all the participants, 72% of them actually prefer an informative companion over a sociable companion. And among the remaining 29% of people, it was more evenly split between those who preferred a companion to be more informative versus those who preferred a more sociable companion. Here we suggest that perhaps those who rely on human assistance might prefer an informative companion because they actually see companions as a tool to assist human staff, while the human actually fulfills the sociable role. And those who rely completely on a companion actually require the companion then to fulfill this social function that humans tend to do. Based on all these results, we've actually developed two companion personas. So the robot companion that you see on the left represents the ideal to have. So it's more sociable, personable, proactive, and it takes a humanoid robot form. And the virtual companion is more impersonal, informative, and because it is screen-based, it tends to be more passive as well. So this represents the must-haves. In conclusion, we've identified some key design requirements for a virtual and robot companion. And we found that the perceptions of companion roles tend to influence their requirements that participants selected. And lastly, the preservation of social connections is crucial with total automation. For our future work, we are further working on developing the companion HMI concepts for autonomous buses using emotional design. This concludes my presentation for today. Thank you very much for your attention.
Hello everyone. My co-authors and I developed a novel approach to the elicitation of requirements in very early design phases. We applied it to the development of specific vehicles for autonomous mobility on demand in urban areas. Private cars are an important economic factor as well as a symbol of personal freedom. However, they are also responsible for air pollution, congestion, and space usage. Public transportation, on the other hand, is more sustainable but lacks flexibility, privacy, and comfort. A possible solution is autonomous mobility on demand, where users are transported by autonomous shuttles on any desired route throughout the usage area, thereby increasing the utilization of vehicles while maintaining privacy and comfort and flexibility. So far, few prototypes like the Vision Urbanetic or the Easy Mile, here's a pilot project in Berlin, exist. Optimal usage profiles, technical layout, and customer benefit are still unclear. However, decisions concerning, for example, infrastructure and the legal framework need to be made today. In this case, foresight tools such as scenario technique are a proper approach. The key of this tool is analyzing possible future conditions, not by just one visionary assumption, but by estimating the effects of as many opposing trends and assumptions as possible. Thereby, a much more reliable framework for decision-making can be created. In our approach, we use features of the scenario technique to shed light on the requirements for autonomous shuttles. Our approach features 4 phases. First, the ecosystem of the vehicle concept is aggregated from literature. Second, 3 consistent scenarios representing different application modes and boundary conditions for the vehicles are derived. These are generated in an expert workshop. Thirdly, the behavior of influencing factors within the scenarios is analyzed, hence generating initial requirements. Fourthly, these initial requirements can be mapped onto design drivers to create specific requirements. Subsequently, vehicle concepts that are suitable for the different scenarios can be developed. The vehicle ecosystem is the basis to identify relevant influencing factors. 7 groups of influencing factors are identified. Users consume the mobility service. The operator owns the vehicles. Traffic and infrastructure, which includes the road and its control facilities, surround the technology. Further away, but still with high interdependencies, are the society, regulations, and the environment. 3 scenarios have been developed. The first scenario describes the coexistence of autonomous and non-autonomous vehicles. Like today, most of these vehicles are privately owned. The infrastructure is mostly incapable of communicating with vehicles. Autonomous shuttles are operated only by the public transportation operator due to legal restrictions. The second scenario implies major political and regulatory changes in favor of autonomous mobility on demand. Private vehicles are banned from inner-city roads. The public transportation operator is the largest operator of autonomous shuttles, but there is a number of smaller operators entering the market. In the third scenario, public transportation will be completely replaced by autonomous mobility on demand. This puts a focus on shuttles with higher capacity to handle the large mobility demand using the existing road infrastructure. By analyzing the scenario-specific requirements from each environmental factor for the first scenario, a list of 70 high-level requirements was generated. Here's an excerpt of that list. It is noticeable that there is no adjustment of the maximum speed in the operation area. Accordingly, the shuttles must also be able to reach the speed. Another interesting point is that the traffic infrastructure cannot communicate with these vehicles. Therefore, sensors that recognize, for example, traffic lights are absolutely necessary in the vehicles. Since the legislation remains unchanged, the shuttles must adapt to the current guidelines for conventional vehicles. This study is just the first step into a new area of research. We will consolidate our scenarios by better exploring user wishes with a conjoint analysis and by broadening our influencing factors. Afterwards, vehicle concepts for all scenarios will be developed. This will reveal, on the one hand, vehicle characteristics sensitive to use case specific changes, and on the other hand, the ones which remain constant. The identification of the robust characteristics and the range in which the others vary allow for much more detailed strategy and infrastructure planning, the creation of a specific legal framework, and a simplified early planning of the technology itself. For further information, I would like to refer to our paper. Besides, I'm pleased to answer all of your questions personally. I thank you for your attention and wish you an exciting and successful remaining time at the Design Conference 2020.
Exploring Challenges with Designing and Developing Shore Control Centers for Autonomous Ships by Henrikke Dybvik, Erik Veitch, and Marcin Steinert. Consider all the stuff around you. I'll bet you most of it was shipped here. Shipping is one of the oldest industries in the world. It connects the globe, letting us transport stuff from A to B. But sometimes we take it for granted that it's the captain and the crew that make this possible. But new technology means that we will soon have ships without the captain and crew on board. In other words, ships are about to get a huge software update. We are currently at the very start of a transition to unmanned ships, autonomous ships. And that's a great thing, right? Well, not so fast. When we say autonomous, we really mean only for a given voyage. The predefined conditions of a voyage can be represented by a dotted line. To work in the real world, the system must be flexible to all sorts of possibilities that might be outside this dotted line. In other words, what happens when something unexpected happens? There is also the issue of safety and environmental responsibility. International rules say that a person, not a computer, must be responsible for a ship. So the question is, how can we make autonomous ship systems flexible to the real world? Well, one solution lies in what is called a shore control center. This is where the captain and crew can supervise and monitor a fleet of autonomous ships and even take over control remotely if needed. We think designers and engineers have an important role in making sure shore control centers are made correctly. All right, so let's build a shore control center. How hard can that be? Well, one major obstacle is that there aren't even any design guidelines out there for this. Shore control centers for autonomous ships represents a whole new design problem in the marine industry. One of the best ways to understand a new problem is by talking to experts. So that's what we did. We interviewed 9 experts to get the latest thinking on autonomous ships so that we could build the tools to tackle the shore control center design problem with more confidence. Here are some of the highlights of what we found. First, experts put things in context. They said shore control centers should be designed incrementally, that is, in stages. The shore control center really represents an integration of existing technologies. Experts then helped us uncover key design goals for the shore control center, with the main goal being able to handle emergencies remotely. Next, we looked at what experts said about design needs. We found out that the key challenge was related to getting operators in the loop, that is, giving them access to enough information to understand a situation, even when under time pressure. Then we looked at concept development and discovered that VTS, or Vessel Traffic Service, which exists today in coordination centers all around the world, offers a really good starting point for shore control center design. We then looked at how experts were approaching the design problem. We found that they were referring to a theoretical model of human cognition called situation awareness. It says that understanding a situation involves three things: gathering information, understanding that information, and projecting that information into the future. Finally, we looked at design specifications for shore control centers, and one of the clear results was that a certified captain and crew must be the ones working at the shore control center, at least at the start. Okay, let's wrap this all up. What do these results really mean? For example, we can start with the VTS format and with a crew of certified seafarers, with the main goal that they must also be able to handle emergencies using remote control. We can use situation awareness theory to investigate how operators get in the loop during such emergency takeovers. We also need to keep in mind that this process is incremental. It is based on continual testing and refinement to see where the most effective solutions lie. This leaves us with several testable hypotheses. Looking ahead, systematic testing will unlock solutions to shore control center design challenges and will be necessary for regulatory approval and user acceptance. That's it for now. Thanks for watching.
Hello everyone. Welcome to a short introduction to our paper on the value-sensitive design in the development of driverless vehicles, a case study on an autonomous family vehicle. My name is Robert Graubaum. I'm with the Institute of Control Engineering at TU Braunschweig in Germany, and we do research on the design of automated vehicles. The work presented in our paper is part of the research project Unica Agile, which aims at developing and showcasing 4 new fully electric driverless vehicles by 2022. The project consortium consists of 16 university chairs and is joined by 8 industrial partners. And the project is sponsored by the German Federal Ministry of Education and Research. Of the 4 cars that are developed, we are using the autonomous family vehicle AutoElf as a case study in our paper. AutoElf aims at serving as a private butler or nanny, being in the position of a specific family and providing mobility, especially to those family members who cannot drive a car on their own in public traffic. In a previous work, we identified some subsidiary tasks the automation system has to fulfill in addition to the driving task in order to actually replace the human driver in a family car. And examples for that are sketched on the slide, like health monitoring, trip planning, or easy access. The design of functionalities to fulfill these subsidiary tasks can be described by using the reference process outline shown on this slide. Our paper describes a stage of design where the functionalities are still in the concept phase, so in early iterations of the overall design process. So at one point in time, we already collected our ideas and use cases and wrote down the functional specification in an item definition. Subsequently, we were able to form a first set of functional requirements, but still leaving a lot of open questions, especially regarding the ethical implications of having functionalities like health monitoring or remote surveillance of vehicle interior. In order to include these ethical considerations systematically in an item refinement, we applied value-sensitive design following Friedman and others. In order to create new input for our functional specification and identify additional requirements, we discuss a conceptual investigation in our paper. The investigation aims at finding relevant stakeholders and their involved values, as well as potential value trade-offs. Aiming at validating and augmenting our value analysis, we also provide an outlook on empirical investigations, which basically describes applying qualitative and quantitative methods from social science. 2 of our findings are that accessibility is a core value of our target user group, and that there are many potential conflicts between the value of safety and other stakeholder values like mobility. In order to provide an input for the system design stage, these findings have to be translated into specific requirements for the system under development. And this is basically the content of our paper. Finally, we provide a mapping of all types of value-sensitive design investigations on our reference process outline. So in addition to the already known conceptual and empirical investigations, there are also technical investigations, which we would see inside the system design stage, and that ask what system design aspects are required to meet value properties and how specific technologies affect value trade-offs. And to conclude this short introduction of our paper, I can provide some recent impressions of our interior design. On the left side is a rendering of the final vehicle interior, and on the right side is our seating box that allows us to test interior components before the final vehicle is ready. And with that, I want to thank you for your attention, and I look forward to receiving your questions.
Okay, Professor, your microphone is muted. So
Yes, okay. Yes,
now it's
thank you very much for your presentations, for the video. So you're welcome to ask some questions. I don't see too many questions here, but you can think about it and ask, and you can go live if you want. You can request, and Mario Boom back there will allow you, and then you can ask questions. I have some questions myself.
yes.
Okay, to the first speaker, to Ralf Stetter there. Well, maybe could we have the? I don't see the pictures of the. I think all the presenting authors. You could turn your camera on, please.
Okay, but I'm here. I'm not sure if someone is missing, but it looks rather complete.
Yeah, okay, but I don't see them. How come I don't see them? Let me see. Okay. So I'm the only one who don't see them, but that's fine. If I'm the only one, let me see. I don't see them. Why? Okay.
You don't see the presenters, or?
No, I don't see the presenters.
Okay, we see them all.
See them, but
so
okay.
For us, everyone is visible.
Yeah.
Okay, good. If everyone is visible, that's fine. So, Ralf, I have a question for you on your paper.
Okay.
Did you do any, in the fault-tolerant design there, did you do any risk analysis of this in the system design? Is that something that you do? And is that important that you consider this, is my question for you.
Exactly. I mean, it's strongly connected. But right now, if you have real-life design problems, the methodology is not there yet. You could do I mean, there is a lot of literature out on risk assessment, but if you have a technical system in a conceptual phase, it's still rather difficult. It's easy if you have the final concept. So if you have a car has this and this components, then you can work with risk assessment rather well. But if you are early, if you think, oh, how do we do the solution? You don't know everything about the solution. It's still a bit fuzzy. And that's something, it was not directly in this paper, but we are working on this. So I think especially risk assessment in the early phases is one main prerequisite for fault-tolerant control.
Okay. And how far are you to test it on the physical system, or you're still in the prototyping and simulation phase?
I mean, that's a pity because of COVID. Usually the car would have started in August, but I mean, the car is nearly ready. I think it will be, everything sort of was a bit slower now. I think the car will be finished in November, but we had test drives already in March, and I think we will test drive again, and they look promising. But for us, we have to prove it on the racetrack, and that will happen next year.
Next year, okay, very good.
Yeah. Mm-hmm.
Very good. All right, the Finny. Now, you did my virtual companion.
Yes.
What are your next steps, and how you? I saw at the end that you have the scenario, right? You propose a Android or a robotic, and then you have more of a big screen. Which one do you think is going to be has been the most popular? Will be the most popular, and what will be your next steps after this?
Thank you for your question. So actually, we did actually do a follow-up study to this one to kind of compare different robot forms as well, to kind of see which ones people would prefer. And I don't know, it was a bit surprising actually that people mostly felt comfortable with the screen-based form factor. We wonder whether that's because of, for instance, familiarity, or the fact that people don't know how to approach a robot yet, or they think the technology is not there to understand them. Because some people would say, give answers such as, if I want to get information, it's faster to do it by myself with a screen, but talking to a robot will take more time. So I wonder how this also compares to if you asked, would they use the screen or human service staff? That could be something to explore as well. But in terms of like really taking the design further, we are trying to explore how the space within the AV itself can be used as an interface. So for instance, how the AV drives, how it talks to people in terms of announcements, or how it shows information can actually also be expressed through different personas of AVs. So it's kind of like combining both companions that you saw just now into the body of the AV. So that's really what we'll be doing in the next few months.
Okay, very good. Thank you very much.
Yep.
I have yes. Any questions? I don't see any questions coming from the chat there. Please go live if you have some questions. That'd be fine. Okay, nothing so far. Now, for the third paper, who was the third presenter here? And that would be about me. I was wondering, did you try the solution neutral? Because in your scenarios, you have different scenarios, and then you look into a solution specific. We've done some research work on the value of solution neutral, and was wondering if you consider this. I guess it would be more at the functional level before you get into the solution specific.
Exactly. Thank you for your question. I hope
you see what I mean. Okay.
I hope I understood it right. But
yes, go ahead. Go ahead.
Okay. So our idea is that we analyze different scenarios that are completely different in certain aspects that are important for the designing of the vehicles. And what we try to do is finding out which parts of the design, so which requirements for the vehicles, stay the same over the entire scenarios. And this will give us a set of requirements that can be, or a set of specifications of the vehicles that can be developed now, and decisions that have to be made upon these specifications can be made today because they don't vary across different scenarios. So maybe this is somehow this neutral design that you were talking about. So this is definitely an important part of what we are trying to find out with this research work.
Okay, good. Can I open the floor now to some of the everybody, but particularly the presenters? Do you have questions for the other people? But what I noticed in this format of conference is that the presentations are very short. So don't be afraid if you have some questions one to each other, because you all presented. Please go ahead.
I have a question.
Yes, go ahead.
Yeah, can you hear me, by the way?
Yes.
Yeah,
Cool.
we can hear you well, and we'll come back to you, Alexander.
I had a question for Penny, because I was very interested in this concept of robotic companions. But I'm interested in why. I'm interested in your point of view of why we need a companion on board in the first place. Just on a more basic level, what's the need for a robotic companion?
Yeah, thanks for your question. Well, for me, the starting point is really because our case study is really about a public bus that is going to be autonomous. So one thing that we noticed is that, maybe without this human driver there, it will kind of change the mobility experience for a lot of people. For people like you and me, perhaps it might not change a thing, but maybe for the very old or the young, sometimes having this presence there that, you can rely on for questions, to ask for information might be helpful. And so we wanted to try, and actually the starting point was to try and recreate like this human touch that you have now with human drivers. But as the research kind of went on, I started looking more into this idea of effective mobility experiences, where we talk of the travel journey not just as commuting from point A to point B, but also that it's a whole social experience. Whether you're in a vehicle with other people, by yourself, there's a very different atmosphere there. And what we want to try and do is to try and manipulate this environment to create different types of mobility experiences. And so that's why I say we're kind of moving away from having like one companion or the other. We try and combine it into the entire environment of the vehicle to see how that can kind of create different experiences for travelers in the future.
Yeah, cool. Very interesting. I'm curious if you have an idea for a robotic companion for a autonomous boat. Do you think we need to have our own robotic, our own theme, like our own maritime theme, or should it just be like a screen-based one?
I mean, that could be interesting. I mean, if you look at a lot of sci-fi, I guess all these ships, right, in space, they kind of have some kind of computer that talks, so that people kind of rely on to get things done. So maybe a similar experience could be something people already expect, when they have all these ideas there. Or it could be, just the ship itself could have a personality, right? You could have a really speedy, aggressive one. You could have one that kind of just floats around. That's kind of how we see at least our buses going. So maybe you could have something similar on the sea, in the sea. Yeah.
Very interesting. I don't know if you saw. Yes, we have Alexander and then Ralf. But maybe a quick comment is that. In the book on sprints, they do a robot for room service in a hotel to bring toothbrush and toothpaste and different things. I think that could work well, but I think there is a learning phase for anybody to do this. I mean, so you need to learn that. Okay, Alexander, you had a question, please.
Thank you. My question is also to Penny, because we also look at the environment within the vehicle and the user experience in some other research work that we do. And one thing that always pops up is the additional use of the time while being in the vehicle. So some people like to work in the vehicle or do some shopping or something like that. Is that also something that you consider when talking about this or researching about this companion in the vehicle? Is that also something that could be used for additional uses of the time within the vehicle?
Thanks for your question. So not, I would say not exactly that we're looking at how people can use their time, but the mobility scenario is definitely one of the considerations that we have now moving forward. So it's actually part of my PhD research, where I try to see how different types of travelers whom we identify through the development of personas, how that combines with different mobility scenarios to give us different experience goals. So from there, we want to see, for instance, maybe persona A wants to maybe have a quiet journey on their way to work. Maybe they also want to do some work on the way there. So we can create like one type of experience. And then maybe for, say, a senior citizen, they might want a more relaxed trip where they can look outside maybe. So again, that changes with the types of trips that they're taking. And that will also influence how we design these different experiences.
Very interesting. Thanks a lot for your answer.
Thank you.
Ralf, you had a question.
Yeah, it goes also to Penny, but I would maybe think about the ship. I think for the ship, the companion would be a barkeeper. That would make most sense. But just kidding. But I'm thinking about a social companion with some social activities. I wonder what are examples which are not annoying. I would be afraid. I could not really imagine a machine making something for me which is socially nice. You have some examples what could be there, some idea?
So do you mean like a deliberately annoying one that tries to provoke?
No, I just would be afraid that it could be annoying for me. I'm not sure. I have not yet made the experience that something like this could be nice. Maybe do you have an experience when a social robot could be nice?
So this reminds me a bit of another study that I did where we also showed different scenarios to people, and they would see the scenarios twice. So once with the screen-based virtual companion and once with a physical robot companion. And then we kind of asked them which one they preferred after that. And one participant actually pointed out that he hated this robot. Every time he encountered the robot in the scenario, he would be like, no, don't come and talk to me. Like he would just like be so annoyed, like, oh, this thing is gonna approach me again every time I see it. And so he kind of anticipated that, and he actually got really annoyed with it. So I think really this reminds me also about some studies that have been done that show that people's personalities also influence how they react to robots or interfaces, and how when people see robots, they kind of expect this kind of human-like social interaction, and so people who are maybe more on the introverted side of personalities, they may not want to interact with a robot and they would prefer a screen, while someone who's more extroverted might be more comfortable with a robot in that sense. But of course, there's a lot of work that's already been done on that, and it's also something that I try to consider in my own work. Yeah.
Okay, thank you.
Henrique, you had a question. Yes, go ahead.
Yes. By the way, I'm also a co-author with Erik on the ship paper. So just so you got that covered. I do like the idea of the barkeeper on board the ship being the robot interface. I actually think that could be a very cool idea. Well, the shipmen are kind of old school, so. But when it comes to you, Fanny, I was wondering if you did any demographic data when you did these surveys. So if you were able to see any correlation between preference and between, for example, age or the type of travel that you discuss.
Thanks for your question. For this particular study, unfortunately, I didn't really go too much into the participants' background. From what I can remember, I think there were no clear trends, but I would have to relook the data again. And this is actually something that I do want to look at in this ongoing study that we have, where we do kind of ask people at the beginning to take this like mini personality test. I think it's based on it's called the Big Five or something, but a very short version. Yeah, and so we plan to use that to kind of see how that affects their responses to the different companion concepts.
Very, very cool. I think I think it's a really good idea to collect more demographic data with the preferences and see if there are any. Well, I expect there to be some kind of correlation in some places. Yeah, very cool. Have you also looked into more? The Big Five is not really developed by psychologists, so there might be other works that are better for benchmarking, say, personality or preferences and such things.
Definitely, I'll look into it. Thank you.
Oh, another thought that occurred is that I think there's been some research on the way that we interact with our computer, the laptop, and that we do those sort of interact same manner as we do with people, because we usually have the one computer and we use it for so much so that it becomes sort of an integrated part of our lives in a very personified way, even though it's still, you know, a computer.
Mm-hmm.
Which is interesting.
Okay, very good. I have a couple of questions. If now, first I'd like to tell Erik and Henrikke, I guess, I don't know who's the draft, the sketcher here, but it's a very nice presentation style. I really enjoyed it. But can you tell us a little more about the situation awareness method that you talked about?
Yeah, sure. I'm happy to. And Henrikke, feel free to jump in if you wish. Yeah, what we found was that experts in autonomous ships, they tended to point us towards this cognitive model of understanding the world around us. And this doesn't really. This goes back to Plato. This really goes down to understanding, making meaning from our surroundings, really. So it's not, this idea of situation awareness is just one way to model how people make meaning from our surroundings.
And it's also it's important to mention that Ensley's work has had a lot of impact, so that it is situation awareness by Ensley that all of these participants referred to.
That's exactly where I was going with that. So there's a very simplified model that was put forward by a researcher called Micah Ensley. And she basically modeled this human's way of making meaning from our surroundings with boxes and arrows. 3 boxes, 3 arrows. And that is, so three levels, basically. The first level is just taking in information with our senses. The second level is making that information understandable, and the third is projecting this understood information into the future somehow. So a basic example might be, you're driving towards an intersection, and you see that the light is shifting from red to green. From green to red. You see that with your eyes, but then you have to make an understanding of it. So you need to stop before going out into this intersection and colliding with a vehicle. But then you need to also project that information into the future. How fast am I going? Is the street wet? If I slam on the brakes, am I going to slide, or do I have time to stop, or should I just go through? So that's a sort of a classic example of Mike Ensley's 3 levels of situation awareness for making decisions.
Very good. Well, in fact, when you were talking here, I used to be a military pilot in my 20s, and I did a lot of flight instruction. And situation awareness is very, very critical when you pilot an airplane, because you need to have this all the time in your. And in fact, we had a way to describe when a student was getting behind in the situation awareness. We're saying, well, he's sitting in the tail of the airplane. He cannot react fast enough. He doesn't interpret things correctly. So it is extremely important. So I can see for ship piloting that it's exactly what it is. And it might be a good input for autonomous car driving and that, because I think it's well, I guess that part, the part that you described, comes from the car, the example that you gave there. So it's quite very interesting. Thank you very much for this. Any other questions? Because I have certainly an important question to ask, because I'm very interested. I do some research on value-based decision making, and I saw a paper yesterday funded by the Daimler-Benz Foundation on this, and it's extremely interesting. Now I saw value-sensitive design. And this is of great interest, and I think that this is by Robert can answer this, right?
Yeah, so you're talking about the paper from Ottawa and Stanford on the workshops on value?
No, there was it was I will find it there. There was a paper yesterday that I found. Let me. Oh, I will. Please answer my question, and I will look for it. Okay, go ahead. Well, what is value-sensitive design?
Yeah, so basically that is just a framework to consider human values in throughout the development of any information system as its roots lay. It's, I think, from the early 2000s, from the researcher Friedman and her team further developed throughout the years. And yeah, basically we also came to that overall approach through the value-based decision-making project of the Daimler-Benz Foundation.
I see.
In collaboration with Stanford and the University of Ottawa.
Okay.
And so our paper now describes a lot of things that came together in our research, because the development process you saw was from the early 2000s from advanced driver assistance systems. So we now try to apply that to also other vehicle systems, like the interior design. In addition to that, we have these approaches for considering human values in our decision making, and now try to also get these approaches ready for the overall vehicle design. So that is basically all that came together there. Yeah.
No, very good. Very, very interesting. Excellent. Thank you very much for the answer. Any other questions coming from the panel itself? Yes, go ahead, please.
One question also to the, I call it chip team. I wonder that the notion ergonomics never did appear, because when I would think, how do I make what you call a shore control center? I think, does it look like a ship or like the inside of a ship, or will it be totally different? So is this also a part, or, I mean, there will be some controls, obviously, and some screens. And do you think it will be like the replica of the inside of a ship, or totally different?
I guess a good start. You're pointing to one of the exact challenges that occur with putting the control of a ship to shore. Much of the infrastructure on the ship currently, for example, the ship bridge, which is basically a long room, and then you have controls on either side and a bigger control in the middle. And that is to be able to steer into harbor on either side, because when you're standing on the middle, you can't see anything except for what's straight ahead of you. And that's a big opportunity as well, because you have the ability to redesign the entire interface and all of the controls to what's best. The problem there again is that we don't know what's best. We don't know how to best control a ship when you have the ability to monitor, say, the ship from so and so many different angles. And you also have access to sensor information from the engine, from the ship side, and from everything that you can think of. And there have been different tests, but they're all still on the prototyping level, and they're usually screen-based. They do not replicate the entire ship bridge. That would actually require quite some space as well, depending on the ship, because they're quite large. Yeah, and then you also have the opportunity to monitor several ships, and there's also an ongoing discussion on how many ships can you actually control, and how should you control them. And the whole monitoring situation, because that's basically what that's one of the important scenarios to do work on, is how to effectively monitor several ships all at once while maintaining situation awareness.
Okay,
So
because for
that's,
me, I think already, because I think most people on ships are standing while they're working their controls. And the question is, will it be sitting or standing? But I think you are working on all these questions.
Absolutely. As far as I've seen, they include chairs in their prototype. So I assume they're kind of, it seems that people are advocating for if you have a screen-based, computer-based layout, then you should sit. But I haven't seen anything on people comparing standing to sitting. But I do know that the blood flow through your brain is about like 7% better when you're standing up, so that you have like more capacity. You have more brain capacity when you're standing up, whereas when you're sitting down. So in that sense, it would definitely make sense to stand up.
Yeah, but maybe you have to control 5 to 10 ships all a whole day. So, but it's an interesting challenge. Thanks a lot.
Yes.
Thanks for your question.
Thank you.
Okay, good. Thank you. I have a question for you all. What do you think, what is the most important part that changes from the normal design process because you're working with autonomous systems? Is there anything in the conventional design process that changes? And what is it? And we can go in the order. I guess we're missing one presenter here.
Erik will be back as soon as he can find a power outlet.
Yeah, okay, yeah. But I mean, if you're there, that's fine. We're 5, okay. Can we go first? Let's start with our fault-tolerant team.
Okay, so I think for autonomous system, the design is changing in this. I think that the electronics part and the part that the system has to be aware about the surroundings is really important, and that's not an add-on. So I think if we take the design process as usual, and I think then we put some intelligence in the end, that's the wrong approach. I think from the initial stage of the system, we have to be aware it is a system that has to function on its own, and the sensing of the environment is so important that I think it's the first thing to decide. Then you can think about the rest of the system.
Very good.
I think that's an important change.
Excellent. Could we go to the next one? 30 seconds, right? Because I think that we're very tight on time here. 30 seconds. Penny, I guess you're the next one.
Yeah. Well, I guess one big challenge is that we are dealing with a future technology, so people don't really have experience with it yet. And so for me, one question I always find myself asking is how valid are these answers that I'm getting? We conduct so much research with users, but it's difficult to say how valid they would be once the actual product is out. They're actually riding in vehicles because, as you say, there's a learning curve, right? So maybe actually with all these questions about acceptance, it's not too big of a problem once people kind of get used to it. And so that's just this big open question I always have with me.
Okay, so Alexander, please.
I will continue what Penny just said. So it's a future technology and we have to plan ahead. This is very important, but also when the technology is here, also when we are able to have autonomous vehicles on the road, it still will be a technology where planning ahead will be a lot more important, since we give a lot of control to machines, and that means that there's no control mechanism in the vehicle in the end that can handle some faults that are within the design. So we have to handle all these things ahead, and that means that we will eventually have to plan a lot longer for future eventualities, for future things that might happen. This is probably the biggest change that I can identify.
So you see a very, very important control loop back, and continuous improvement is as a fundamental nature of the system design, right?
Definitely.
Is that what you're saying?
Control loop, definitely, but also we need more planning ahead. So we need to identify things that might change in the future conditions, so we can plan our design for these changes today.
Okay. Okay.
because there's nothing in the vehicle that will react to these changes other than the machine that we designed today.
Okay, all right. So okay, we go with Henrique and Erik. I'm asking, what do you think changes? What's the most important part of the design process that changes with autonomous vehicles?
So I think what Ralf said was pretty much to the point, that the type of sensing and the type of automation that needs to be included in concept development and design. But then later on in the design process, this also needs to be tested. And this testing and this iteration becomes even more important because interaction with autonomy is so different from all of the interactions that we currently do. And so figuring out that is going to be very different and also very important to design autonomous vehicles well.
Okay, thank you very much. Erik, you want to say a few words quickly?
Yeah, sure. Just very quickly, I can add to this train of thought. Yeah, I think, what changes are going ahead for design? I think a really big thing is, I mean, it sounds pretty fundamental and obvious, but this idea of human system integration, it all seems to come down to getting engineers, especially, to learn new tricks, to learn about the human experience part of the system. And we all need to learn more. Designers also need to learn about the importance of what happens inside these black box autonomous systems. About learning and working together in multidisciplinary teams for human system integration.
Okay, very good point. Thank you. And Robert, you have the last comment.
Yeah, I guess I don't have to repeat too much what the others already said. So just from my own research background, I would phrase it in a way that I say, think about the release as early as possible. There's been showcases of driverless vehicles for 50 years now, and there's actually no point in piling up resources to build prototypes and showcase something that has been showcased before if you cannot respond to the question how you would ever be able to bring that to the road.
Okay, all right. So you need to put the previous design into the thing. Well, thank you very much for excellent presentations and exchange here. It was very dynamic, and I really appreciate it. I'm sure it was great for everyone, and it's being recorded, so you never know where it's going. And congratulations for your paper, and looking forward to see you again. Bye-bye, everyone.
Thank you. Bye-bye.
Okay. Thanks to everyone.
Bye.
Bye-bye.
Thank you.
Let's give a hand to the champion.
Yeah, thank you, everyone. Thank you.
Okay. Goodbye.
Bye-bye.
Okay.